Let us work with the atoms. And of course, the most famous C2B molecule is water. We have talked about water. Okay. Symmetry operations are the same, but let us use this O and oxygen atom and the hydrogen atoms as the basis. Now, hydrogen atoms do not really have A and B written on them, but then we have to write a matrix, right. So, if I write H and H, it will be very confusing. So, let me use the labels A and B. Let us pretend for a while that we can make out between the red colored hydrogen atom and the blue colored hydrogen atom. Okay. And here I have just written A and B. What will be the matrix for E for this basis? No matter what the basis is, matrix for E remains the identity matrix, right. And in this case also we have a basis that is 3 dimensional. So, here also we have 1 0 0 0 1 0 0 0 1. Okay. What about C2? What happens in C2? O remains O. O would better remain O for everything, isn't it? No matter what we do, if oxygen becomes hydrogen, then either it is not a symmetry operation or you are a wizard of nuclear transmutation. Okay. Since we are not, oxygen would better remain oxygen. Fine. Now, what happens to A and B? They get interchanged. So, let us write the matrix now. 1 0 0. What will be the second line? 0 0 1, right. So, see now what has happened? You have gone off diagonal. The 1 has gone off diagonal, right. Why? Because A has become B, B has become A. What is the third one? 0 0 1? No, 0 1 0. 0 1 0. A and B have interchanged. Convince yourselves that this is the correct matrix. Are you convinced? Good. Now, what about sigma zx? Sigma zx should have the same matrix as E, right? Same 1 0 0 0 1 0 0 0 1, right? What about sigma v dashed yz? Again, O remains the same, A and B interchange positions. So, the matrix will actually be the same as C2, right? So, now can you block factorize this? What kind of block factorization should we do? Where should we draw the lines? Remember, all the 4 matrices have to be split in exactly the same way. Where will we draw the line? No, I will draw a horizontal line and a vertical line, but where? First wala? First row, first column. After first row, after first column, like this. Huh? Now look at the blocks. Maybe remove 0 and look at the blocks. So, we have 1 by 1 block and we have a 2 by 2 block. The thing is, when we talk about classes, we talk about irreducible representations only. Okay, right now I do not know at this point. Well, I actually know that the second one is a reducible representation, but then officially in this class we do not know whether the second one is reducible or irreducible. If it is reducible, then the question of class does not arise. Alright. So, these are the blocks. Do you all agree that this is how we should draw the lines, right? Once again 1 by 1 matrix and we have a 2 by 2 matrix. Okay. So, write them. So, now what do we have? We have 2 representations. The first one is 1 1 1 1. No matter what you do, this guy is so stubborn that he is not going to change, right? 1 1 1 1. So, this is a 1 dimensional, therefore irreducible representation. Okay, understood? And it is actually a special kind of irreducible representation. All the characters are 1, which means, so what is the basis here? O, right? Which means no matter what you do, no matter which symmetry operation you bring in, O does not change. O does not change means what? Character of 1 means it is symmetric, right. So, O is symmetric with respect to all the symmetry operations, right. So, when you have a representation like this, everything is 1, then you call it the totally symmetric representation. It's 1 1 1 1 or 1 1 1 or 1 1 1 1 1 1, whatever it is. If all the characters are 1 or if all the numbers are 1, for now let us say that, then that is called a totally symmetric representation. The basis of this representation is symmetric with respect to all the symmetry operations that you use. Okay. And of course, it does not mix with anything else, that also is an issue. It is a one dimensional representation. Are we okay with this? Okay with the block factorization? Okay with the concept of this totally symmetric representation? Sure? May I move on? Right. So, moving on, we have to think about this one. This is a two dimensional representation, right. Is this a reducible representation? Is this an irreducible representation? So, the question that I am essentially asking is this, are these 2 by 2 matrices diagonalizable or not? This is diagonalized, this is diagonalized, these two are not. So, how does one diagonalize matrices? So, one way of doing it is similarity transformation, isn't it? But then it is not all that easily done, okay. But you can still try to do it and find out whether this is diagonalizable or not. So, that is the first question, okay. At this point, without doing anything else, I do not know whether this is reducible or irreducible. With the benefit of hindsight, I know that it is reducible, that is a different issue. But prima facie, looking at this, it is not so easy to tell whether it is reducible or not, okay. And the second question that comes to us at that time is that total how many such irreducible representations are there? How many reducible representations can be there for a given point group, symmetry point group? How many reducible representations? I am asking a general question. For any symmetry point group, what will be the total number of reducible representations? Reducible representation. Yeah. So, first many and then realization dawns, and the correct answer that comes is infinite. I can take the reducible representations and I can combine them in whatever way I want. I can just keep on increasing the number of the elements in the basis, right. If I have all the time in the world, I can generate an endless number of reducible representations, okay. That is infinite. But what about the number of irreducible representation? I should have written irreducible here. How many irreducible representations are there? Is that finite? Is that infinite? Can we determine what it is? The answer is yes, it is finite, and the answer is yes, we can determine how many irreducible representations there are, okay. But how do we know that? Okay, doing similarity transformations over and over again for everything, that is not such a nice thing to do. So, that comes from something called great orthogonality theorem, and great orthogonality theorem arises out of a group theoretical treatment of this problem of symmetry operations. So, that is what we are going to learn in the next few classes, right. So, the plan of the thing, first of all, I am sure many of us know what groups are, but I am also sure that many of us are rusty on this, okay. So, but then if I say that I do not learn anything, so nobody will tell me anything. So, let us try to learn this together, okay, learn, recapitulate, whatever. So, first let us introduce ourselves to what are groups. Second, let us convince ourselves that symmetry operations of a molecule or of a symmetry species actually form a group, okay. That is why group theory works, because symmetry operations in a symmetry point group actually form a group, what is called mathematically a group, okay. This is not a senior group, junior group, high CPI group, low CPI group, not like that. Or so this is group as defined mathematically. Okay, fine. Next is that if you have to do that, then you better know a little bit about matrices. Once again, everybody has studied, but old people like me have forgotten. So let us remind ourselves that also. A little bit about matrices, how to diagonalize a matrix, what is the matrix eigenvalue equation, what is a unitary matrix, what is a Hermitian matrix. Please do not get scared hearing unitary and Hermitian. These are nothing that we cannot handle. We will do it slowly and we will learn together, alright. And then that will prepare us for this group theoretical treatment of transformation matrices, fine. Hence, we reach our primary goal, the great orthogonality theorem, and as we will see, great orthogonality theorem will tell us, will answer all these questions that we have. How many irreducible representations are there? What is the dimensionality of each of these representations? And then finally, what are these representations? Everything you can work out once you have mustered enough courage and crossed this activation barrier posed to you by group theory and matrices. Okay? It will take us maybe a little more than a week to get here. Okay. From there, we will work out the character tables as promised, and then what we do is, after that we are back in chemistry. For the rest of the semester, we start talking about applications in chemistry. We talk about molecular orbital theory. Before that, we will talk about something called symmetry adapted linear combination, and then we will talk about bonding by and large. If time permits, we can talk about molecular vibrations, right. So, that is the plan of what we are going to do.